Thank you, Tony, again for organizing. Very excited about this. This is my first virtual presentation, so please excuse any bumps on the road. So I'm going to be talking about a model of costly recall today. It's joint work with Spencer Kwan and Yoran Ma, both of whom are here today with us, and they'll be also on the Slack board taking questions. So just thinking a little bit about the motivation that we had for this project, we were interested and we were intrigued by the now a well-documented set of facts about how beliefs react to news. In particular, we're interested in the literature on overreaction of beliefs to news, which is usually documented in the case of stock markets, and more recently in terms of individual forecasts and survey data. So Euron's previous work with Bordalo, Schleifer, and Giannoli has documented this. And just to expand a little bit on this, I'm going to go over what I mean by overreaction. But basically, we have two stylized facts that we're going after in this paper. One is the fact that overreaction seems to be stronger in beliefs when the underlying process that agents are trying to forecast is less persistent. And also it seems to be stronger when the horizon of the forecasts that they're making is also longer. So really, like the question that we're asking is that what explains these facts about overreaction? So traditional models of expectation formation, we have models that predict overreaction to news. In fact, like one of the first models of expectation formation, which is adaptive expectations, would give you overreaction in to news. But what these models fail to capture, and what seems to be a characteristic of the forecasts and the data and necessary to understand, is the variation of the degree of overreaction with the parameters of the environment, and also the horizon, which is not a parameter of the environment, but the way that the agent is thinking about the future of the process. So what we're going to do in this paper, we want to link a micro-founded model of memory and recall that is grounded in empirical evidence on how memory works with these patterns in the data. So we're going to write a micro-founded memory-based theory of overreaction, which is going to generate this variation that we're after in terms of horizon and persistence. And then we're going to use experimental data from Landier, Ma, and Tesmar to basically test the predictions of the model and see how the model fits. Now, there's going to be some unique characteristics of this survey that's going to help us to kind of go after these predictions that I'm going to talk about once I get to the experimental component of the talk. So just before going into anything, I want to talk about what we mean by overreaction. So usually in models that we're thinking about in survey forecasts or in any forecasting environment, the way that overreaction is defined is that we're thinking about an agent who observes a fundamental process. So for example, this could be inflation, this could be stock returns, this could be anything, GDP growth. We're going to call that XT. XT is like a symbol of these things that the agent is trying to forecast. And what you're seeing as the agent in the environment is some measurement of this process. So we see I don't know, PLS comes up with a statistic about inflation, or we see prices, or we see some returns, and we want to make a forecast about different horizons of this process. So here I just have it as XT. And the idea is that just looking at it from a best linear predictor perspective, what do we expect beliefs to look like? So basically, there's going to be an ex post belief that is exposed to observation of news, and there's going to be an ex ante belief, which is the prior and before, and comes before the observation of the news. And the relationship between these two usually is thought of as the ex post belief is the ex ante belief plus some loading on the news component of the observation. Now, the one thing here is that this XT minus the prior captures the surprise element of the observation X. So like just seeing that GDP is 2% may not be any surprise to anyone, but seeing how it deviates from what we thought it's going to be is going to have an impact on my beliefs. So this can come out of, for example, a common filtering framework, if you want to think about it that way. And then the sign of this lambda is going to basically put us in different, or like the magnitude of this lambda is going to put us in different realms of research. So just to start from a benchmark, if we live in a full information rational expectation environment where we observe all the shocks and we see what's going on in the world, we expect this lambda to be 1. If I see exactly what GDP is, and it doesn't matter what my prior was, all that matters is what the truth is. So that's kind of like the benchmark that people define overreaction and underreaction. Underreaction is going to be when lambda is less than 1. So the loading that I have on news is less than what a rational agent with full information would put on the news. And like if you want to think about a model that generates this, like the classic models of sticky or noisy information, where you see a noisy observation of the truth, and then like you do a common updating framework on it, will give you this. And you can already see that why those models are not good models of overreaction, because we're gonna call this overreaction if all of a sudden lambda is bigger than 1, and any common filtering environment or any sticky environment will give you that lambda is between 0 and 1, so we can't really generate overreaction with this. But officially, the way we're defining overreaction is lambda larger than 1, okay? And here you need to come up with ways of thinking about the world that does not really fit into that noisy information framework anymore, for example. And one example of like the models that generate this, again, like you can get this from adaptive expectations if you want, or if you want like more recent modern micro-founded models, diagnostic expectations models is a way of getting this. But really what we are after in this paper is not a model that generates lambda bigger than 1. That's kind of like a necessary condition for the paper, for the model that we're trying to write. But we want a model that explains how a lambda larger than 1 increases with the horizon of forecasts and decreases with the persistence of the process. So that's kind of like the novelty of the model that we're going to write here. Not the first to write a model of overreaction, but as far as we know, we're the first to go after how overreaction varies with the environment and trying to write a model that understands that. Now, I want to go over a very conceptual framework of how I thought about it when I started doing this project that really helped me to categorize different models of belief formation and how we fit in this world. So if I want to conceptualize how micro-founded models have been thinking about belief formation, we usually have an environment like this that there's an environment out there that draws us the history of shocks. There's a working memory, which is like on the part of the agents, and the agents observes something about the history of the shock. So this is like what we call the perception channel. Or in cognitive science, they would call this encoding. Like you see something in the world, and then there's like a image of that thing in your mind that you perceive, and that's going to be your observation of the world. And then there's going to be an expectation formation process that's going to take that image and map it to a belief. And so noisy information models, for example, so let's just start from the rational expectations with full information. So full information means that you perceive everything perfectly. If X is 5, you see 5. And then rational expectations means that you take that 5 and in a model consistent way, you map that 5 to a belief. Now you can already see that by putting a friction on the perception channel is not going to give you any overreaction. So I can make you fully observe the world, or I can make your observation or encoding noisy. And the more noisy I make your perception, you're going to be less trusting of what you see in the world. So what you see in the world is the news, And if I make your news noisy, then you're going to become less trusting to the news and more trusting to what's already in your memory. And that's a story of underreaction. That's a story of, I really trust my prior. I don't really want to trust this thing that I just saw. So if we want to go after overreaction in a framework that fits into kind of like in this kind of thinking, we need to add something else. We need to add a balance between what I see in the world and what is there in my memory. And for that, we need to kind of separate this concept of working memory, where accessible things, accessible observations for beliefs live, from a concept of a long-term memory that kind of stores what I have experienced in the past, what kind of observations I have seen in the past. And immediately when we separate that from the working memory, then we have two new channels. One is that, how do observations from working memory get stored into long-term memory? And then given that the storage, how are those recalled when I need them? Okay. So today, I'm going to only talk about a recall channel. So suppose the storage is again free, and I'm just going to be talking about recall. Note that like just adding this channel doesn't change belief formation. It's still consistent with full information rational expectations. I can write a model, put a long-term memory in it, and as long as I have no frictions in terms of what you can store and what you can recall, then I have just made your simple rational expectations model with full information much more complicated, but the result is still the same. What really adding this component helps us is that now I can take the friction from the perception channel, put it on the recall channel, and then think about what the implications of that is going to be. And the implications of that in our setting is going to be overreaction. Because now I see exactly what's going on in the world if there's no friction in the perception channel, but I'm less trusting of what is there in my mind. And I'm going to underweight what's in my mind and overweight the news that I observe in terms of what it predicts for my future. So that's what we're doing. We're just going to take a simple model. We're going to take everything to be frictionless except for this recall channel. Okay. Now, how do we, just a brief literature review. So we're going to model how we think about recall in this framework after the empirical literature on how memory works. And there's a literature there which is memory is subject to certain frictions and recall is subject to certain shortcomings that creates bias in belief. And we're going to combine that with a process of conscious recall where I understand that what immediately comes to my mind when I see lowest stock returns might not be representative of what actually is happening. And I have the choice to exert effort and think about my observation a little bit harder and try to go back to more data points in my past and correct the biases that this instinctive recall is introducing for me. So the conscious recall component is going to be very similar to like models of rational attention, with the twist that we're taking this perception and perception channel and we're putting the friction on the recall channel. So there's a theoretical and empirical literature on documenting the patterns in underreaction and overreaction, which is going to guide the facts that we're trying to match. And there's a theoretical and experimental literature on memory and beliefs, which is going to guide how we think about modeling this world. With that, let me tell you a little bit about the model. So before going into equations, I want to tell you about what are the frictions that we're putting in this environment. What are the facts about memory that we're trying to match? And then I'm going to tell you a little bit about how we're going to take advantage of those in our model. So the main fact that we're going to take into account is that research on memory has shown that recall is subject to association and recency. So association and recency basically means that whenever I'm put in a context, so like the context can be, I wake up today and I see that the stock returns are low or stock prices are just plummeting. And what happens, that's going to immediately recall some memories or some observations that I had in the past. And association and recency means that I am more likely to remember similar episodes or more recent episodes. So if I saw like stock market like go down yesterday, that's more likely to come to mind than if I saw it a year ago. And also, I'm more likely to remember all the instances that I saw stock market to go down versus all the instances where the stock market went up. Now you can see that this will have a biasing effect in the sample that I'm recalling. First of all, I might be subject to small sample bias if the number of memories that I can remember is limited, which is going to be introduced as noise in our framework. But also, if I'm more likely to remember all the instances that the stock market was going down, then it means that I'm going to assume and I'm going to think that this is it. This is like stock markets are going to be low from now on, if that's the only thing that I'm thinking about. Now, of course, the fact that the first thing that comes to my mind is the fact that the stock market went down doesn't mean that I should be naive and trust all that observation to be the truth. I might know that my memory is subject to these frictions. I might know that what's happening in my mind is that I'm remembering the stuff that are similar to this episode. So I might have an incentive to go and try to remember stuff that would correct that bias. And that's going to be a conscious recall process that we're going to call. So our model is going to be an agent trying to balance these two. So you have a free recall process. It's great because it's free. It's not good because it's biased. It reminds you of things that are similar, and it's going to make you to do things that are not optimal from the perspective of a person who knows everything. Then we're going to have a conscious recall process. It's great because it's not subject to those biases anymore. You can remember stuff as unbiased and as precisely as you want. But the catch is that it's now going to be costly to do that. It's really like it's really easy to remember things that are similar, but then to sit down and think about, okay, I am remembering things that are similar, so let me remember like instances that has nothing to do with this episode that I'm going through, but are useful in predicting in terms of what's going to happen in the future. So you can already see that the free instinctive recall is going to make me to put a lot of weight on the observation, because that's kind of anchoring my mood and my beliefs and how I think about the world. But at the same time, you can see that how the conscious recall process is going to partially correct for this. And that partial correctness, or how much incentive I have to go and remember stuff that are going to correct that bias, is going to depend on the marginal return and the marginal cost of remembering unrelated memories. And you can see that this is now going to give us the variation that we wanted in terms of persistence and horizon. So if I want to remember things to make a longer run forecast, I might have different incentives. And if I want to remember things to forecast a more persistent process, I might have different incentives to do that. So that's basically, this is like the heart of the model. This is just going, like from now on, it's just going to be writing a framework that kind of like takes this and puts it into a maximization framework. Okay. So here, let me just show you like the environment. For today's presentation, I'm just going to go through a very simple example, like the simplest example that we can write with this, which is an AR1 process. In the paper, like the paper itself is still like work in progress, but we already have a more general setting there. For the purpose of like this presentation, I think this example is perfectly fine. I need an AR1 process because I want to vary this row. This is going to change the persistence of the underlying process for me. And I need time because I want to think about horizon. But other than that, it's a very simple forecasting problem. So the agents are forecasting this AR1 process. What is their payoff? So they're going to have a quadratic payoff in terms of they're going to make forecasts about the value of this AR1 H periods ahead. So that's going to be like their action. ATH means that I'm making a forecast about horizon H at time t. And the payoff that I'm going to get is how accurate my belief is compared to what a rational agent with full information would predict. So the idea is that, so like that if y bar is equal to 0, this rational forecast is rho to the h times today's observation. So this is from the perspective of a person who has no memory frictions, has observed all the shocks about this process, knows exactly what's going on. So what is the assumptions on what our agent can observe? So we're going to assume that our agent observes yt at time t. We're going to assume that they know rho, because we don't want to like start with a model that has a biased rho that's going to kind of be assuming the result. We want to assume that even in a world where the agent knows what the rho is, what are the frictions and what are the results that we're going to get out of these memory frictions. The only thing that we're going to assume out of the ordinary is that we're going to assume that our agent doesn't know y bar. Now, in a classic model where everything you see goes into your memory and you have a bank of data points that goes back a very long time for this process, that might seem an odd assumption that y bar is not something that the agents know. Because as long as I have like a large enough sample of like these data points, I can easily predict what y bar is. But the point is that we are trying to write a model that the fact that you have seen stuff in your life doesn't mean that they're readily available for belief formation. So these YTs are somewhere in there in the back of this guy's mind, but he needs to exert effort and go extract those data points and try to use them to form a belief about y bar. So when I wake up at time t and I want to think about this process, y bar is not in the front of my mind. I need to think about it. And that thinking is costly. That's the idea. So what is the timing? So at time t, this guy is going to wake up. There's going to be an instinctive recall that is going to happen instantaneously. Basically, I'm going to wake up, I'm going to observe YT, and that YT is going to induce a prior about Y bar for me. That's going to be just a distribution of Y bar conditional on YT. Then I have the option of recalling more stuff, which we're going to call conscious recall. So what is this conscious recall? The conscious recall is a signal that can be generated by the history of like by the history of the realizations of the AR1. So I have seen all the stuff that has happened in the past. Let me put all of those in this big YT. That's in my long-term memory. I can retrieve stuff from my long-term memory, but that's going to be costly in a second. Given that I retrieve RCT from my long-term memory, then I'm going to act in a perfectly Bayesian manner. I'm going to add that RCT to my previous observation, which was the context, and I'm going to form a posterior, which is going to be the distribution of Y bar conditional on YT and the stuff that I just recalled from the past. What is the cost of recalling stuff from the past? We're going to assume that that's proportional to Shannon's mutual information. This is just a way of measuring information. So this function is going to take RCT. It's going to measure how much RCT reminds me of Y bar, conditional that I already have seen YT. So that's kind of like think about this as a function of the joint distribution of RCT and Y bar. And the more correlation there is between them, it means that there's more information revealed by one of them relative to the other one, which means that in order to have that belief, I must have remembered a lot of stuff. And if we want to make that costly, that would mean that I had to pay a higher cost for that. This omega is going to be capturing the degree of the friction. Omega equal to 0 puts us back to a benchmark where recall is not costly. I wake up, I see YT, but I can freely remember all the stuff that has happened in the past. So this kind of nests the rational expectation full information framework. So after that, the agent is going to make the forecast based on the posterior that they have. So what is the problem that they're solving? So the problem is a two-stage problem. So let's do it with backward induction. After I remember all the stuff that I need to remember, all I need to do is to make a forecast. And I'm going to make my forecast to minimize the distance, the quadratic distance between my forecast and what a rational agent with full information would do, because that's my payoff. That's going to be conditional on an R bar T set, which is my total recall. Total recall is just the context plus whatever like I remember through conscious recall. The second stage, the first stage, which comes before making the forecast, is how much I want to remember about Y bar. Okay, and that's going to be that I don't know what forecast I'm going to make, but in expectation, I know what payoff I will get from that forecast being more precise. So I trade that off with the cost of remembering the stuff. So if I remember more stuff, I'm going to make a better forecast. That's good for me. But I'm going to pay a higher recall cost. I have to sit down and really dwell in my past, and I don't really like doing that. The solution to that is going to determine how much I want to remember from this RCT channel. Now, what does this framework give us? So let's first talk about the extensive margin. So in this framework, you're not always going to want to remember stuff other than the context. So like deploying this conscious recall process itself is a decision, and there's a corner solution for that. So we can show that this conscious recall process is going to be deployed if this condition is holding. But let me tell you what that condition is telling you. It's telling you that, first of all, the most obvious case is that it's going to be more likely for me to deploy my conscious recall if omega is low, meaning that like recall is not very costly. So that's the obvious one. The more interesting result, number one, is that I'm going to deploy this if I'm facing a sufficiently small row, sufficiently small persistence. So think about, I see YT. If I don't remember anything through conscious recall, I'm going to take YT as a representation of what this process is going to be from now on. Now, if I'm facing an IID process, that's really bad, because I shouldn't really do that. I shouldn't take YT to be a representation of what the process is going to be from now on. So for lower rows, I have a higher incentive to deploy conscious recall and try to remember what the mean is. If I'm facing a random walk, of course, I don't really care. Like YT is what the process is going to be from now on. And finally, I'm going to deploy the conscious recall. I'm more likely to deploy it if the horizon is long, the horizon of my forecast is longer. This is really simple to see when you think about horizon 0. If somebody's asking me what the process is right now, I don't need to remember anything to say that. I exactly observe what YT is. But immediately when I start going to longer horizons, it becomes more and more important for me to remember what that Y bar was. And in order to remember what the Y bar was, I need to go back and remember stuff from the past. So then in the intensive, so that was the extensive margin, but the intensive margin also has a similar frame where we can show that, let me normalize Y bar equal to 0. It doesn't really matter. Subtract Y bar from both sides of the forecast. Then the average forecast for horizon H is going to be, forget this minimum for a second, is going to be rho H plus a term times YT. Now remember that the rational agent with full information would just tell me rho H times YT. But my agent here is putting an additional weight on YT, which comes from the fact that they don't know a lot about Y bar, and they have to partially rely on YT to predict what Y bar is going to be. And that is, that depends on what omega is. If omega was 0, I could go back and remember all that stuff. But if omega is really high, I need to partially take YT as what the process is going to be in the future. So you can see that how the model generates like these two observations. So we were going after persistence, and how lower persistence means that you remember more stuff and overreaction is lower. and then also how longer horizon forecast had also an effect on overreaction. Now, I have 5 minutes left. In this 5 minutes, I just want to go over like how we fit this model to the data. So the data that we're going to use for this is an experiment from Landier, Ma, and Tesmar 2020. What they do, they basically give participants exactly the process that we assumed for the model. So that was no coincidence, obviously. So they're going to have like an AR1 process. The great thing about this experiment and why we think it's superior to survey data, for example, is that, first of all, we know exactly what the underlying process that these guys are forecasting is. Second of all, we know exactly what they've seen in the duration of their forecasting life, as opposed to like in the survey data, we don't really know what's in memory and what's not. And then finally, another interesting part of it is that they vary rho. So we can actually see how forecasts and degree of overreaction changes with rho. So participants are going to see this AR1. They're going to be randomly assigned to be either in an environment with rho equal to 0, rho equals to 0.2, and like if they're going to go until 1. And they're going to make forecasts for 1 period ahead and 5 period aheads of the process. So like there's also like 2 periods ahead, but we're going to focus on this 5 periods ahead, 1 and 5. They're going to have access to 40 past realizations, and they're going to start forecasting for 40 rounds. Now they're going to like the thing that they see these realizations is going to be something that is I view this as something that's helpful for us because it's in front of them, but it doesn't necessarily mean that they exactly know what those data points mean for the long run average of the process. They have to think about it. And that's exactly what we're going after. How much do you want to look at that data and think about it? That's the incentive channel. So what we're going to do, we're going to take basically this equation that I had in the model, and we're going to estimate this in the data. So we know what the true rho is, and we see forecasts, so we can estimate what the implied rho is. So we're going to call this term here from, like, we're going to run a regression like this, and we're going to call the term that we identify on YT as rho hat. Sorry for going back on the slides. And then we're going to compare rho hat with rho. So just starting from the data, this is coming from the data. On the x-axis, I have the actual persistence of the process. On the y-axis, I have the implied persistence of the process. Okay. What do I see? I see that the implied persistence is larger than the actual persistence. Okay, so that's the overreaction story. That's the fact that people put a larger weight on YT than what a rational agent with full information would do. What else do I see? I see that as I increase persistence, the distance between the 45-degree line and the implied persistence gets smaller, which is going to be another fact that we're after. Now, for longer horizons, so this solid blue line was for 1 period ahead forecast. Now the dashed line is for 5 periods ahead forecast. And the message from this that I want you to take away is that overreaction in the 5 period ahead forecast is larger than the overreaction in the 1 period ahead forecast. So the implied rho is above the solid line for 5 period forecast. Now, we can take our model. Our model has one parameter that we can fit to the data, that's omega. So we're going to take the solid blue line, which is the 1 period ahead forecast, and we're going to choose 1 omega to fit this curve. Okay. So the first observation is that the model does a really good job in fitting this curve. Okay. Now, like, that's not really clear until I show you how the other models would fit. So the red dots are our model, and then we have very different models, so like multiple different models here. I want to talk about the sticky information model. So that's these like little crosses under the 45-degree line. So remember that I was talking about how sticky information model would give you underreaction rather than overreaction. And you can see it here, even though that we're trying to fit that model to this data, it miserably fails and predicts even underreaction, even like rather than overreaction. The other one that I want to talk about is adaptive expectations. So adaptive expectations have been there for a long time. We don't like them, but they're still a really good benchmark to think about them in different projects. So these little diamonds here are how the adaptive expectation model fits to this data. And you can see why it's not a really good fit, because if I want to fit, it's going to give me like basically a line with an intercept. And if I want to fit this part of the curve, I'm going to miss here. And if I want to fit this part of the curve, I'm going to miss at the higher end. What our model adds on top of that is that it adds this incentive channel that you're more likely to remember stuff and deploy conscious recall here than here. So we're going to get like an endogenous curvature that's going to help us fit this. Then I can take the persistence. So this was my in-sample fit. I can do also an like out-of-sample untargeted moment kind of exercise by saying that I now have an omega from this 1 period ahead forecast. Let me plug that into the model, make 5 period ahead forecasts, see how that fits with the 5 period ahead forecast data, and that's this curve. So again, our model generates this higher overreaction and longer horizons, even though that like we're not really trying to fit this. There's nothing in the data, nothing in the model that tries to like fit this, but it naturally arises because when agents are trying to remember farther horizons, these memory frictions are going to move them in the right direction that we see in the data. Again, I can try to fit other models. Like our models fit is like the best. So
we're starting. Yeah.
Conclude. Yeah. Sorry about the couple of minutes. So just to conclude, we wrote a model that tried to match this 2 facts about how beliefs react to news based on horizon and based on persistence. And we tested that with experimental data. Thank you so much. Sorry for the going over time.